Picture this. It's March 1989. Astronauts up on the Space Shuttle Discovery suddenly notice a hydrogen tank sensor showing some wildly high pressure. Just a normal glitch, right? Or how about October 2003? Scientists are down here watching the SHO satellite, and suddenly their cameras fill up with what looks like dense, white snow. In both cases, they totally thought they were just dealing with run-of-the-mill equipment malfunctions. But they weren't. What they were actually witnessing, in real time, was the brutal impact of a massive solar storm. Welcome back, Focus learners. In today's explainer, we are diving into the invisible threat of solar storms, satellites, and the vulnerability of our modern power grid.
So what happens when that snow on a camera or that broken sensor isn't just a random glitch? It means we're caught in the crosshairs of the raw, awesome power of our sun. When the sun unleashes that energy directly at Earth, it literally threatens our entire technological existence. It's a huge wake-up call that our modern systems are constantly under an invisible cosmic threat.
All right, let's dive into Section 1, the sun's explosive tantrums.
So, how does a storm on the sun actually reach down and mess with us here? It all starts with a coronal mass ejection, or a CME. You know, the sun is basically this giant, rotating, tangled mess of magnetic fields, right? Well, because its equator spins faster than the poles, those magnetic fields get seriously twisted and stretched out. Eventually, they get so contorted they literally snap and reconnect. Think of it like twisting a rubber band until it just breaks. This magnetic reconnection triggers a colossal blast, hurling billions of tons of high-energy charged particles and magnetic fields straight out into space.
When those twisted fields snap, it's not just a quick flash. They trigger intense X-class solar flares, which are the absolute biggest category we have. And those almost always come with these massive CMEs. You're not just looking at light, it is a physical shockwave of radiation and charged plasma hurtling across the solar system at literally millions of miles per hour.
Let's trace the journey of one of these storms. The initial explosion happens right at a sunspot. Then, that CME travels across space and absolutely slams into Earth's protective magnetic shield, our magnetosphere. The sheer force of this impact actually compresses the magnetosphere. That rapid change induces massive electrical currents that flow through the Earth's ionosphere and eventually right down through the ground. This is what we call geomagnetically induced currents, or GICs, and they end up totally saturating our electrical infrastructure. It is literally a direct chain reaction from a solar explosion straight to the power lines on your street.
Moving right along to Section 2, satellites in the crosshairs.
Okay, so space is our very first line of defense, but it's also where some of our most vulnerable tech lives. When a storm hits, high-velocity solar protons act like microscopic wrecking balls. As they blast through a satellite's semiconductor devices, they create electron-hole pairs that can actually flip bits of memory. Engineers call this a single-event upset, and it leads to phantom commands. Plus, they bombard star tracker sensors, totally confusing the navigation. On top of that, the storm heats up Earth's upper atmosphere, causing it to swell outward. This creates a ton of atmospheric drag on low Earth orbit satellites, slowing them down and making them lose altitude incredibly fast.
To survive this absolute barrage, engineers on the ground have to take some pretty drastic measures. When our early warning systems spot an incoming wave of intense radiation, operators will intentionally power down non-essential and highly sensitive equipment, basically putting the satellites into safe mode. This is exactly what they had to do during those intense 2003 Halloween storms, just to prevent catastrophic hardware failures across dozens of different orbital missions.
Let's bring this down to the surface in Section 3, attacking the power grid.
What's really wild and kinda ironic is how our own infrastructure actually works against us here. Our high-voltage power lines are super long and grounded at substation neutrals. During a solar storm, they basically turn into giant loop antennas. They scoop up those geomagnetically induced currents flowing through the Earth's surface and channel them straight into our large substation transformers.
And the physics behind how these fail is fascinating. Since these GICs are super low frequency, they act a lot like a direct current or a DC bias, entering an alternating current or AC transformer. This DC offset drives the transformer's magnetic core into total saturation. Once that happens, you get these incredibly spiky AC waveforms and extra electrical harmonics that completely confuse protective relays, causing them to suddenly trip power lines. Even worse, the saturated core causes catastrophic thermal overheating. We're talking literally melting the copper coils right inside the transformer.
Now, geographically, this risk is definitely not evenly distributed. Because Earth's magnetic field funnels these charged particles toward the poles, high-latitude regions like Canada and Sweden face way more exposure to these ionospheric disturbances. But during a truly extreme Carrington-level storm, that auroral danger zone expands dramatically toward the equator. That pushes severe grid vulnerabilities into normally safe lower-latitude places like Texas, or, as we actually saw during the 2003 Halloween storm, all the way down into South Africa.
So let's look at some of those past heavyweights. We are moving to Section 4, Historic Solar Storm Chaos.
Scientists measure the intensity of geomagnetic storms using the KP index, which is a global scale that maxes out at a 9. Take a look at this comparison. The 1859 Carrington event is our baseline extreme. It literally set telegraph stations on fire, which is basically the 1800s equivalent of your Wi-Fi router suddenly bursting into flames. Fast forward to March 1989, a massive KP9 storm hits, completely collapsing the Hydro-Quebec power system and plunging 6 million people into total darkness for 9 hours. Then, the 2003 Halloween storms. Another KP9 event damaged the SOHO satellite, caused blackouts in Sweden, and physically destroyed 12 transformers down in South Africa. It just proves that lower-latitude grids are absolutely in the line of fire.
Which brings us to Section 5, the May 2024 event.
How does a modern disturbance stack up against those historical giants? Well, the May 2024 event was born from active region 3664. This was a sunspot group so unbelievably massive that it actually surpassed the physical size of the sunspot responsible for the 1859 Carrington event. This single region generated intense X-class flares and fired off a rapid succession of at least 5 Earth-directed coronal mass ejections right at us.
The data we got from this was just staggering. Unlike typical storms that peak and fade pretty fast, during May 2024, the KP index stayed at or above an extreme level of 8 for a full 24 hours. The interplanetary magnetic field dropped drastically, and the auroral zone expanded so far south that you could literally see the northern lights in Puerto Rico. Up in Canada and globally, aviation faced major degradation of high-frequency radio and GPS-based GNSS navigation. It was basically a prolonged, unrelenting stress test for our modern systems. But hey, there is good news here. Let's head into Section 6, Predicting and Protecting.
Unlike in 1859 or even 1989, we are not flying blind anymore. Today, we've got a seriously robust defense playbook. Forecast centers, like the Canadian Space Weather Forecast Center, use satellite data and numerical modeling to track CME propagation times down to the minute. When they see a big storm coming, they issue global alerts. This gives airlines time to reroute polar flights to lower magnetic latitudes, which protects passengers from radiation and maintains communication. Meanwhile, power engineers are busy physically hardening the grid by installing series and neutral blocking capacitors that literally stop those geomagnetically induced DC currents right in their tracks before they can enter the transformers.
National disaster prevention agencies analyze these threats in specific tiers to help manage long-term grid reliability. You've got your breezes. These are mild storms happening multiple times a year that just cause a bit of thermal degradation and require standard maintenance. Then, gales hit every 5 to 10 years like in 1989 or 2003. Those trigger safe modes, memory upsets, and flight rerouting. But the ultimate focus? That is preparing for the hurricanes, the 100 to 150-year Carrington-level events. By studying recent data from the May 2024 storms, engineers are actively building resilience to prevent widespread grid collapse when that next massive solar hurricane finally strikes.
It really is amazing to step back and realize that an explosion happening 93 million miles away has the power to dictate whether the lights stay on in your house or whether a satellite survives its orbit. We're so deeply, invisibly connected to the tantrums of our star. We rely entirely on incredible human engineering and rapid forecasting to just keep our technological world spinning. It really makes you wonder, as we become more and more reliant on fragile electronics, are we truly ready for the next 100-year hurricane? Think about that the next time your GPS glitches. Wild, but true.